Something is happening to Earth. Our planet's magnetic field, the invisible shield that's kept us safe from the sun's radiation for billions of years, is collapsing. The South Atlantic Anomaly is spreading, and far below our feet, Earth's core is behaving, unlike itself. All this is happening at the exact moment an interstellar object, 3I Atlas, is racing past the sun. Coincidence or cosmic choreography? The timing is too perfect, too precise to ignore. And history has taught us one thing. The cosmos doesn't do coincidences, so stay until the end, because what we uncover tonight might just prove that harmless was never the right word. If this mystery has you hooked the way it has me, make sure to hit like and subscribe so you don't miss a single update as this unfolds in real time. Drop a comment with where you're tuning in from, what time it is there, and what you think about this new development. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this, so thank you for having our back. Part 1, Flashpoint. Right now, as you listen to these words, something ancient is failing. Earth's magnetic field, the invisible force that has cradled life for billions of years, is weakening at a rate that has scientists pulling all-nighters and checking their instruments twice. And today, October 29th, 2025, at precisely 11:47 Coordinated Universal Time, an interstellar visitor named 3I Atlas reaches its closest point to the Sun. If you live in Nairobi, Kenya, that moment translates to 14:47 local time. Scientists assure us these two events share nothing but timing. They tell us correlation does not equal causation, but here we are, standing at the intersection of two cosmic events that make the hairs on the back of your neck stand up. And you have to wonder if the universe is trying to tell us something we're not equipped to hear. The numbers don't lie, even when we wish they would. Since 1840, Earth's magnetic dipole moment has dropped by roughly 9%. That might sound gradual, almost boring, until you realise we're talking about the protective bubble that keeps solar wind from stripping away our atmosphere the way it stripped Mars down to a barren rock. The weakening isn't uniform either. There are zones where the field has collapsed so dramatically that satellites passing overhead experience radiation exposure levels that would have seemed impossible just decades ago. The South Atlantic Anomaly, a region stretching from South America to southern Africa, has expanded to cover nearly 1% of Earth's surface. That's an area roughly half the size of continental Europe where the magnetic shield has thinned to dangerous levels, and it's been growing aggressively since 2014. Meanwhile, 3I Atlas traces a hyperbolic arc through our solar system, coming from somewhere in the galactic neighbourhood we'll never visit. This is only the third confirmed interstellar object we've ever detected, after Oumuamua confused everyone in 2017, and Borisov reminded us what a normal comet looks like in 2019. Atlas was discovered on July 1st, 2025, by the Asteroid Terrestrial Impact Last Alert System survey in Chile, though pre-discovery images stretch back to mid-June. At perihelion today, it passes approximately 1.36 to 1.4 astronomical units from the Sun. That's about 200 million kilometres, well beyond Earth's orbit. In December, it will make its closest approach to our planet at roughly 1.8 astronomical units. No collision risk, no gravitational drama, just a cosmic passerby that happens to be spitting water vapour and dust far from the Sun where comets shouldn't be active yet. Scientists working on geomagnetic data don't talk to scientists tracking interstellar objects very often. The fields barely overlap. Geophysicists study convection patterns in molten iron 3,000 kilometres beneath your feet, driven by heat left over from Earth's formation and the radioactive decay of elements you can't pronounce. Astronomers point telescopes at faint smudges moving against background stars, calculating trajectories and spectral signatures. These communities operate in parallel universes of expertise. But timing has a way of making strange bedfellows, and when your planet's protective shield develops alarming weak spots at the exact moment an object from beyond your solar system swings past, even rational minds start asking uncomfortable questions. The European Space Agency's Swarm satellite constellation has been mapping Earth's magnetic field with unprecedented precision since 2013. The data they've collected paints a picture that contradicts the comfortable assumption that geomagnetic changes happen on timescales measured in centuries or millennia. Since 2020, certain regions have shown accelerated weakening. A secondary minimum under Southwest Africa emerged and grew faster than models predicted. The North Magnetic Pole, which used to drift lazily across the Canadian Arctic, has been racing towards Siberia at speeds that required emergency updates to navigation models. The World Magnetic Model, used by everything from smartphone compasses to aircraft navigation systems, needed an unscheduled correction in 2019 because the pole was moving too fast for the scheduled update cycle to keep pace. This video will take you on a journey through data that doesn't care about your comfort level. We're going to examine what's actually happening to Earth's magnetic field, using measurements from satellites and ground stations and centuries of navigation records. We'll look at 3i Atlas in detail, from its discovery to its weird polarimetric signatures to the 8 documented anomalies that have some researchers quietly raising eyebrows. We'll explore why mainstream geophysics says there can be no connection between a passing comet and core dynamics. Then we'll ask the harder question: what if there are mechanisms we haven't considered? What if the core is balanced on some kind of threshold state where tiny perturbations matter more than energy calculations suggest they should? Later, we'll wade into speculative territory, flagging it clearly as we go. We'll examine fringe theories and conspiracy threads, not to validate them, but to understand why they emerge. When faced with unexplained acceleration in magnetic field decay and an interstellar visitor arriving right on schedule, human pattern, seeking minds start connecting dots. Some of those dots form pictures that don't survive scrutiny. Others might hint at questions worth asking, even if we lack instruments sensitive enough to test them yet. The line between open-minded inquiry and fantasy can blur, but we'll try to keep our feet on solid ground while our minds wander through possibilities. If 3i Atlas is harmless, if it's just a chunk of ice and rock following the laws of gravity through empty space, then something else must explain why Earth's magnetic field is behaving like a system under stress. The core doesn't know about comets. Convection patterns in molten metal don't respond to gravity waves from objects barely more massive than mountains passing by at astronomical distances. Physics demands mechanism, not coincidence. But physics also demands we look at what's actually happening, even when observations don't fit comfortable narratives. So which is it? Are we watching two unrelated phenomena unfold in parallel? Or is the universe more interconnected than our departmentalized science has prepared us to understand? Stay with me, because this mystery gets stranger the deeper we dig. Part 2. What's really changing in Earth's magnetic field? The planet beneath your feet generates a magnetic field, the way a dynamo generates electricity, except the dynamo is the size of Mars and made of liquid iron, spinning at temperatures that would vaporize steel. This geodynamo has been running for at least 3.5 billion years, protecting the surface from charged particles that would otherwise make complex life impossible. It's not a perfect shield. Solar wind still interacts with the upper atmosphere, creating auroras and occasionally knocking out power grids. But it's the reason Earth still has an atmosphere, while Mars, which lost its magnetic field billions of years ago, became a freeze-dried museum of its former self. When scientists measure a 9% decline in the dipole moment since 1840, they're telling you the dynamo is losing strength in a way that's measurably different from background fluctuation. Magnetic fields change. That's normal. The geodynamo responds to turbulent flows in the outer core, creating secular variation on timescales of years to centuries. The North Magnetic Pole wanders. Compass declination shifts gradually, requiring periodic updates to maps. Geophysicists expect this. What they don't expect is the kind of accelerated regional weakening observed in the South Atlantic Anomaly over the past decade. The SA has been a known feature since satellite measurements began, but its expansion since 2014 represents something qualitatively different. The anomaly now covers millions of square kilometers, where radiation exposure at satellite altitudes exceeds design specifications for electronics. Spacecraft passing through this region experience bit flips and component degradation. The International Space Station adjusts its orientation during SAA transits to protect sensitive equipment. The South Atlantic Anomaly isn't just expanding, it's spawning. Around 2020, researchers identified a secondary weak cell developing under Southwest Africa. This new minimum appeared and strengthened faster than computer models of core convection predicted. The pattern suggests something happening at the core mantle boundary beneath that region, possibly a reversed flux patch where magnetic field lines loop back into the core instead of emerging toward the surface. These patches represent localized breakdown of the organized dipole structure. Think of them as eddies in a river where the current temporarily reverses direction. The difference is this river is made of molten iron 3,000 kilometers down, and the eddies are thousands of kilometers across, and they're interfering with the magnetic bubble that keeps you alive. Northern Hemisphere changes paint a different picture. Canada's historically strong magnetic region has been weakening while Siberia's intensifies. The North Magnetic Pole has drifted from the Canadian Arctic toward Russia at accelerating rates, currently moving about 55 kilometers per year. That might sound slow until you realize it's racing across nearly 700 kilometers per decade. The World Magnetic Model, jointly produced by the US National Oceanic and Atmospheric Administration and the British Geological Survey, is updated every 5 years. Between the 2015 and 2020 versions, the pole moved so much faster than expected that navigation errors would have accumulated to unacceptable levels without an emergency update in 2019. The 2025 model incorporates even more dramatic changes, reflecting a magnetic field that refuses to behave like textbooks said it should. Quantifying the changes helps ground the abstract in something concrete. The South Atlantic Anomaly's area has roughly doubled since the year 2000. Where it once affected primarily the South Atlantic Ocean, it now extends inland over South America and Africa. Magnetic field strength in the core of the anomaly has weakened by approximately 25% in some measurements. Satellite operators now routinely account for increased radiation exposure when planning orbits and scheduling operations. The European Space Agency's Swarm mission, launched in 2013, was specifically designed to map these changes in high resolution. The 3-satellite constellation measures field strength and direction with unprecedented precision, revealing structures and dynamics invisible to ground-based observations. The rate of change matters as much as the magnitude. Geologists studying ancient lava flows and sediments can reconstruct how Earth's magnetic field behaved over millions of years. The paleomagnetic record shows the field flips polarity every few 100,000 years on average, though the timing is irregular. Between flips, the field wanders and weakens, but generally maintains its protective structure. What's unusual about the current weakening is how fast it's happening in localized regions. The decades-long acceleration in the SAA's expansion doesn't match the gradual drift seen in most of the paleomagnetic record. Some researchers describe parts of the current field as changing more rapidly than at any time in the past 1,000 years. That phrasing is careful. It acknowledges uncertainty while flagging something worth paying attention to. Navigation systems worldwide depend on accurate magnetic field models. The World Magnetic Model feeds data to aviation navigation, maritime compass corrections, military targeting systems, and the GPS-assisted compass in your smartphone. When the model falls out of sync with reality, errors accumulate. Aircraft flying polar routes are particularly sensitive to magnetic declination errors because GPS coverage becomes unreliable near the poles and magnetic compasses provide backup navigation. The 2019 emergency update to the WMM was unusual but necessary. The 2025 update incorporates even more substantial corrections, reflecting a magnetic field that continues evolving faster than 5-year update cycles can fully capture. Trying to predict where the field goes next runs into fundamental limits. The geodynamo is a chaotic system in the mathematical sense. Small changes in initial conditions or boundary conditions can produce dramatically different outcomes over time. Researchers run computer simulations of core convection, constrained by observations of current field structure and evolution. These models successfully reproduce some features of secular variation but struggle with rapid regional changes like the SA expansion. The physics is well understood in principle, but computationally intractable in practice. Simulating turbulent flow in a rotating sphere of electrically conductive fluid at the temperatures and pressures found in Earth's core requires supercomputers running for months to model decades of evolution. Even then, the results are approximations. The emotional weight of this isn't lost on researchers who spend their careers studying planetary magnetic fields. This isn't slow geologic drift playing out over timescales that make human lifespans irrelevant. Parts of Earth's protective shield are weakening and restructuring right now during our lifetimes, in ways that could matter for technology-dependent civilization. Satellite operators care because radiation, aviation cares because navigation. But on a deeper level, we're watching a planetary-scale system that has sustained life for billions of years enter a phase that doesn't match comfortable assumptions about stability. Whether that phase leads to a full polarity reversal, or settles into some new configuration, or represents temporary fluctuation that will reverse in a few centuries, remains unknown. The data shows change accelerating, and we're along for the ride whether we understand it or not. Could anything external influence this process? Could variations in solar wind pressure, or cosmic ray flux, or, hypothetically, the passage of an interstellar object somehow couple to core dynamics in ways standard models ignore? Mainstream geophysics says no, the energy scales don't match, the mechanisms don't exist in peer-reviewed literature. But we'll explore that question anyway, because sometimes the most interesting science happens when observations force us to reconsider what we thought impossible. For now, just sit with the fact that Earth's magnetic field is doing something unexpected, and scientists are working hard to understand what that means for the planet you call home. Part 3. What we know about 3I Atlas. Right now, interstellar objects don't announce themselves with fanfare. They appear as faint dots moving against background stars, distinguished from asteroids and comets only by orbital calculations that reveal hyperbolic trajectories, indicating they're passing through rather than orbiting. 3I Atlas entered that exclusive club on July 1, 2025, when the Atlas survey in Chile flagged an object that didn't belong. Pre-discovery images pushed the detection back to mid-June, but the confirmation and trajectory calculation took time. By early July, astronomers had confirmed what the numbers were screaming. This thing came from outside our solar system, making it only the third such object we've ever caught in the act of visiting. The designation tells a story if you know how to read it. The C in C/2025 and 1 indicates it's a comet with a long period or non-periodic orbit. The 3I prefix marks it as the third interstellar object catalogued by the Minor Planet Center. Oumuamua holds the honor of being 1I, discovered in 2017, and still generating papers arguing about whether its non-gravitational acceleration was outgassing or something weirder. 2I/Borisov came next in 2019, looking refreshingly like a normal comet, which somehow made it less interesting to the public, but more valuable to scientists. Atlas splits the difference. It's definitely a comet, showing both a coma and a tail as it approaches perihelion. But it's exhibiting behaviours that don't quite fit the template. Perihelion timing matters for this story. October 29th, 2025, at 11:47 UTC, 3I Atlas reaches its closest point to the Sun at approximately 1.36 to 1.4 astronomical units. That's about 200 to 210 million kilometres. For reference, Earth orbits at 1 AU, so Atlas passes well outside our orbit. The comet's hyperbolic trajectory means it's moving faster than solar escape velocity. Gravity from the Sun bends its path but can't capture it into a bound orbit. After perihelion, Atlas will swing back out toward interstellar space, never to return. In December 2025, it makes its closest approach to Earth at roughly 1.8 astronomical units, about 270 million kilometres. That's more than 700 times farther than the Moon. No collision risk, no gravitational perturbation of Earth's orbit. Just a flyby. Physical characteristics emerge from telescopic observations and spectroscopy. Size estimates suggest a nucleus possibly up to 5.6 kilometres in diameter. That's larger than many short-period comets in our solar system, but not unusually so. The nucleus is surrounded by a coma, the cloud of gas and dust produced when solar heating sublimates ice from the surface. Water and hydroxyl radical emission lines appear in spectra, confirming that Atlas carries water ice like comets originating in the solar system. But here's where it gets interesting. Atlas started showing significant water emission when it was still beyond 3 astronomical units from the Sun. That's farther out than most solar system comets become active. The early activity suggests either a very volatile rich composition or some mechanism heating the nucleus more efficiently than expected. Polarimetric observations add another layer of weirdness. When light reflects off dust particles in a comet's coma, the reflected light becomes polarized. The degree and direction of polarization depend on the size, shape, and composition of the dust grains. Astronomers use polarimetry to study comet dust properties without physically sampling it. 3i Atlas showed a deep negative polarization branch in pre-perihelion measurements, meaning the reflected light was polarized in a way that doesn't match typical solar system comets. The specific pattern suggests unusual dust grain properties, possibly indicating different formation conditions in whatever stellar system ejected Atlas billions of years ago. Photometric monitoring tracking brightness changes over time reveals temporal variations in dust production. The Nordic Optical Telescope contributed observations showing how Atlas's brightness and tail morphology evolved as it approached the Sun. The tail structure includes both a dust tail swept back by solar radiation pressure and an ion tail shaped by the solar wind's magnetic field. At various points, observers noted the tail exhibited asymmetries or structures that suggested uneven outgassing from the nucleus. Comets often do this. As a nucleus rotates, active regions face the Sun at different times, creating jets and fans of material that give the coma and tail a lumpy appearance. But the specifics of Atlas's tail behavior have prompted enough comments in observer reports that it's worth noting as something to watch. Comparative context helps frame what makes Atlas special. Oumuamua confused everyone by showing non-gravitational acceleration without obvious signs of outgassing. Its elongated shape and tumbling rotation were unlike anything seen before. Proposals range from exotic ices to hydrogen icebergs to, in one notable but non-mainstream paper, a light sail. Borisov, by contrast, looked like a comet should look. It had a normal coma, normal dust production, normal composition. It fit models. Atlas occupies a middle ground. It's definitely a comet. The coma and tail prove that. But the early water activity, the polarimetric oddities, and the detailed tail morphology all suggest it's not quite a cookie-cutter version of comets we're used to. Each interstellar object expands the envelope of what normal means, teaching us that planetary systems form objects across a wider range of properties than our single system sample suggested. Perihelion could trigger more surprises. As Atlas heats up at closest approach, sublimation rates spike. Comet nuclei sometimes fragment near perihelion when thermal stress cracks them apart. Atlas's size makes catastrophic breakup less likely, but localized fragmentation or sudden increases in outgassing are possible. Brightness could spike if fresh ice becomes exposed. The tail could develop new structures, or nothing dramatic might happen, and Atlas could just get brighter and dustier in ways entirely consistent with comet physics. Observers worldwide are watching, telescopes pointed, spectrographs ready to catch whatever happens. Then there's the question of anomalies. A recent analysis flagged 8 unusual aspects of Atlas's trajectory and behavior. These include alignment angles that seem statistically improbable, early activity already mentioned, polarimetric weirdness also mentioned, and a few other technical points that make astronomers say, that's odd, without necessarily indicating anything revolutionary. Anomalies pile up in science. Most resolve into measurement error or incomplete models. A few become the seeds of new understanding. Right now, Atlas's anomalies are in that uncertain zone where they're interesting enough to mention but not definitive enough to overturn anything. What Atlas definitely isn't: a threat. The orbit doesn't intersect Earth's orbit. The mass is far too small to gravitationally perturb planetary orbits in any measurable way. This is an observational opportunity, not a hazard scenario. But opportunities come with questions. What can Atlas tell us about the stellar system it came from? What does its composition reveal about planet formation conditions in that system? How common are interstellar objects in our galactic neighbourhood? And, for the purposes of this video, is there any conceivable way its passage could interact with Earth's magnetosphere or deeper planetary systems? Spoiler, mainstream science says no, but we're going to ask anyway, because the timing is too perfect to ignore, and sometimes the universe has a sense of humour darker than we're comfortable with. Part 4. Why many scientists say there is no link. The geodynamo generates Earth's magnetic field through a process that sounds simple until you try to model it. Liquid iron in the outer core convects, driven by heat escaping from the solid inner core and residual heat from Earth's formation. The liquid is electrically conductive. As it flows, it carries magnetic field lines with it, stretching and twisting them, in ways that amplify weak seed fields into the strong dipole we observe. Rotation adds another layer of complexity, organizing the flow into helical patterns. The result is a self-sustaining dynamo that has run for billions of years, occasionally flipping polarity but never fully shutting down. The energy source is thermal and gravitational. The timescale is decades to millennia for secular variation, longer for reversals. Nothing about this process, as understood by geophysicists, invites or allows external triggers from asteroids, comets, or other passing objects. The energy mismatch alone kills most proposals for external influence. 3I Atlas has a mass measured in trillions of kilograms, which sounds impressive until you compare it to Earth's mass of nearly 6 times 10 to the 24th kilograms. The gravitational interaction is negligible beyond tidal effects, so small they're unmeasurable. Even if Atlas passed much closer, say inside the Moon's orbit, its gravitational influence on Earth's core would be vastly smaller than tidal effects from the Moon and Sun, which are already too weak to significantly affect core convection on human timescales. The electromagnetic energy in Atlas's ionized tail, assuming it has one in the context of solar-wind interaction, is trivially small compared to the energy budget of the geodynamo. There's no known mechanism to transfer that energy down through 3,000 kilometers of mantle to where it might matter. Peer-reviewed literature on geomagnetic secular variation doesn't mention comets or asteroids as forcing factors. Thousands of papers model core convection, secular variation, polarity reversals, and anomalies like the South Atlantic Anomaly. They invoke internal dynamics, thermal convection, compositional convection from solidification at the inner core boundary, interaction between the core and lower mantle. External factors occasionally considered include Earth's rotation rate, which changes on long time scales due to tidal friction with the Moon. But those changes are gradual and well constrained. No one has published a credible mechanism by which a comet, passing at 1.4 astronomical units, could influence core dynamics. The timescale mismatch reinforces the disconnect. Magnetic dipole decline has been ongoing since at least 1840, possibly longer. The South Atlantic Anomaly's growth accelerated around 2014, more than a decade before Atlas was discovered. The North Magnetic Pole's acceleration towards Siberia started even earlier. These are ongoing processes with roots in core dynamics that predate Atlas's arrival by years to centuries. 3I Atlas's perihelion is instantaneous by comparison, lasting hours at closest approach. Even if there were some hypothetical coupling mechanism, why would a transient event produce effects that started years earlier and will presumably continue years after? Model-based forecasts of magnetic field evolution, like the World Magnetic Model and the International Geomagnetic Reference Field, assume only Earth internal sources. These models take current field measurements from satellites and ground stations, combine them with decades of historical data, and extrapolate forward using mathematical representations of the field as spherical harmonics. The extrapolation works well enough for navigation over 5-year update cycles, though rapid changes require occasional corrections. Crucially, no terms in these models account for astrophysical events. The math doesn't include comet passages or solar wind variations or cosmic ray flux. It assumes the field evolves according to internal processes alone, and that assumption has held up under testing. Uncertainties exist. Scientists readily admit that physics at the core mantle boundary is less understood than we'd like. The boundary is 3,000 kilometers down, inaccessible to direct sampling, observable only through seismic waves and magnetic field measurements at the surface. Heterogeneities in the lower mantle affect heat flow from the core. The mantle is not uniform. It has blobs of denser material, variations in thermal conductivity, and residual effects from ancient tectonic events. These boundary conditions affect core convection in ways that are hard to model precisely. The appearance of reversed flux patches under the South Atlantic and Africa suggests localized core flow patterns that weren't anticipated. Models are improving, but they're still approximations of a system too complex to fully simulate. The mainstream view is that correlation does not equal causation. Two things happening at the same time don't necessarily influence each other. Earth's magnetic field is weakening for internal reasons. 3I Atlas is passing through the inner solar system because gravity and momentum carried it here. The overlap in timing is coincidence, perhaps striking but ultimately meaningless. Scientists are trained to resist pattern seeking when mechanisms don't support connections. Extraordinary claims require extraordinary evidence, and right now there's no ordinary evidence, much less extraordinary, that Atlas affects Earth's core. But the story doesn't end there. Mainstream consensus is powerful and usually correct, but it's not infallible. Science advances when observations don't fit models, forcing either better observations or better models. The rapid evolution of the South Atlantic Anomaly surprised researchers precisely because it didn't fit comfortable assumptions about slow secular variation. The fact that 3 interstellar objects have now been detected in less than a decade, when theory predicted maybe 1 or 2 per year passing through the inner solar system, suggests our understanding of the local interstellar environment was incomplete. Models are tools, not truths. They represent our best current understanding, constrained by available data and computational power. What if there are mechanisms we haven't considered? Not because scientists are closed-minded, but because the observations needed to reveal those mechanisms are recent or subtle, or require instruments we're only now deploying. The geodynamo couples to the mantle through electromagnetic induction and mechanical interaction. The mantle couples to the crust through tectonic forces. The crust and atmosphere couple through pressure and heat exchange. The magnetosphere couples to the upper atmosphere through auroral currents and particle precipitation. Earth is not a collection of isolated systems. It's a coupled whole, with feedbacks operating across vast ranges of timescale and energy. Could some weak coupling exist between heliospheric conditions and deep Earth processes, operating below current detection thresholds, but occasionally mattering during threshold states? That question leads us into speculative territory. Before we go there, we need to acknowledge the baseline. No known mechanism links Atlas to Earth's magnetic field. The energy doesn't work, the timescales don't work. The physics as currently understood says no, but science is the art of asking what if, even when the answer is probably nothing. The next few sections will explore advanced hypotheses, clearly flagged as speculative, that try to imagine pathways for external influence on core dynamics. Most will fail under scrutiny. That's fine. The point is to think clearly about how interconnected systems work, and whether our departmentalized understanding might be missing something that operates at the boundaries between disciplines. If Atlas is harmless, and I suspect it is, then what's happening to Earth's magnetic field has purely internal causes that we need to understand better. But asking whether external factors could ever matter, even hypothetically, is an exercise worth doing, so let's do it. Part 5. Framing the mystery. Coincidence or clue? Perfect timing unnerves us. We're pattern-seeking primates who survived by noticing when the rustle in the grass correlated with danger, even if most rustles were just wind. Evolution didn't reward skeptics who waited for mechanistic explanations before reacting. It rewarded those who assumed connection and acted accordingly. That instinct serves us poorly in the age of big data, where coincidences are statistically inevitable, and our brains still scream significance at every alignment of random events. Earth's magnetic field weakening while an interstellar comet swings past feels meaningful. The question is whether that feeling points to something real or just reveals our cognitive biases. Let's play with hypotheticals, marked clearly so nobody mistakes speculation for established fact. Could transient charged particle flux from an interstellar visitor alter near-Earth magnetospheric currents? In principle, any plasma injected into the heliosphere interacts with the solar wind and Earth's magnetosphere. Comets produce ion tails when solar ultraviolet light ionizes gases in the coma. The solar wind's magnetic field then drags those ions away from the Sun, creating the characteristic straight tail seen in photographs. If Atlas is producing an unusually dense ion tail due to high outgassing rates, that tail becomes a temporary feature of the local heliospheric plasma environment. Earth's magnetosphere constantly interacts with solar wind. It's shaped by that interaction, forming a teardrop with a bow shock on the sunward side and a long magnetotail streaming away on the night side. Could Atlas's ion tail, if Earth passed through or near it, perturb magnetospheric currents? The answer depends on density and geometry. Earth won't pass through Atlas's tail in any close sense. The closest approach is 1.8 astronomical units in December, far too distant for direct tail interaction. But heliospheric plasma doesn't stay confined to narrow streams. It diffuses and turbulently mixes. If Atlas is injecting ions and dust into the solar wind at rates significantly above background, those particles spread through a volume that could, in principle, include Earth's magnetospheric environment weeks or months later. The perturbation would be tiny. Solar wind variability from coronal holes and coronal mass ejections dwarfs anything a comet could produce. But we're asking about thresholds, about whether small inputs can matter if a system is primed to respond. Another angle involves cosmic rays. Galactic cosmic rays are high-energy particles, mostly protons that permeate the galaxy. They're partially deflected by the solar wind, creating a modulation that depends on solar activity. Earth's magnetic field provides additional shielding, especially at low latitudes. If Atlas carried an unusually strong magnetic field embedded in its nucleus or coma, could it locally alter cosmic ray flux in its vicinity? Could that perturbation propagate through the heliosphere and modify ionization rates in Earth's upper atmosphere? The energy scales seem wrong. Interstellar objects are not magnetized at levels that would matter across astronomical distances. But stranger things have been proposed. Oumuamua's non-gravitational acceleration spawned a dozen competing hypotheses, some more credible than others. Atlas's early activity and polarimetric oddities at least leave room for the question. Magnetospheric currents do couple to the ionosphere, and the ionosphere couples to the thermosphere, and atmospheric dynamics couple to surface climate and ocean circulation, and ultimately everything is connected to everything else through chains of influence that weaken with each link. The question is whether any chain runs from interstellar comet to deep Earth in a way that's physically plausible. Mainstream geophysics says no, because the attenuating factors at each step reduce hypothetical influence to insignificance long before reaching the core. But systems near critical points can exhibit disproportionate responses to small forcing. Climate tipping points operate this way. Ice albedo feedback means a small initial warming can trigger runaway ice loss. Ecosystem collapses can be triggered by perturbations that wouldn't matter in more stable configurations. Is Earth's geodynamo in a threshold state? The accelerating weakening of the South Atlantic Anomaly and the rapid pole drift suggest the field is in a dynamically active phase. Some researchers describe the current configuration as potentially progenitive of a polarity reversal, though timescales for reversals are thousands of years and unpredictable. Reversed flux patches at the core mantle boundary indicate localized regions where the field structure has broken down. If the core flow is organized into competing gyres, with one gyre weakening the dipole and another trying to sustain it, then the balance could be delicate. Small perturbations to boundary conditions, whether from mantle heterogeneity or external electromagnetic forcing, might tip the balance more than energy budget calculations suggest. This is where we slide from physics into informed speculation. No peer-reviewed mechanism exists for comet-induced geomagnetic variability. Proposing one requires either discovering new physics or identifying overlooked couplings in known physics. The latter is more plausible, but still a long shot. Could variations in magnetospheric currents, driven by unusual solar wind conditions or hypothetically by ion injection from a comet, induce electric currents in the mantle that feed back to core convection? The mantle is a poor electrical conductor, but it's not an insulator. Geomagnetically induced currents from solar storms have been measured at Earth's surface, flowing through ground and affecting power grids. Those currents are driven by rapid changes in the magnetosphere during geomagnetic storms. Could sustained low-level variations in magnetospheric topology from an extended interaction with comet plasma produce weak but persistent induced currents deeper down? The energy budget still doesn't close. Currents induced in the mantle by magnetospheric variations are many orders of magnitude weaker than the currents driving the geodynamo. Even if you could somehow couple them to core flow, the effect would be lost in the noise of thermal convection and compositional buoyancy. But maybe that's thinking about it wrong. Maybe the question isn't whether external forcing adds energy, but whether it adds information. A small signal at the right frequency might phase-lock oscillations that are already present, amplifying existing instabilities without adding much energy. Analogies exist in engineering, like how small periodic forcing can drive resonance in mechanical systems. Whether anything similar applies to geodynamo physics is unknown because nobody has looked for it. Why would they? The premise seems absurd until you're staring at a timeline where magnetic anomalies accelerate just as an interstellar visitor arrives. Conspiratorial thinking thrives in the gap between observation and explanation. When official statements say no link, but timing screams coincidence, people fill the void with stories. Some claim secret satellite data exists showing electromagnetic interactions that governments are suppressing. Others suggest Atlas is not a natural object, but something artificial, perhaps a probe or derelict ship from another civilization. A few go full simulation hypothesis, arguing that coincidences this perfect indicate we're living in a constructed reality where such alignments are narrative devices. These ideas range from untestable to falsifiable and falsified. They're worth acknowledging not because they have merit, but because they reveal the psychological need for connection when faced with unexplained phenomena. The fringe speculation around Atlas includes claims that its trajectory has deviated from published ephemerides, suggesting course corrections or undisclosed maneuvers. Reddit threads and YouTube videos analyze publicly available positional data, finding discrepancies that either represent measurement uncertainty, data processing errors, or wishful thinking. NASA and other space agencies have not announced any anomalous behavior beyond the scientific anomalies already discussed. The lack of official comment on internet speculation is not suppression, it's triage. Scientists focus on data that passes peer review, not on every claim posted online. But the silence feeds suspicion, which feeds more speculation, creating a feedback loop that's hard to break without direct engagement. Whether you find these theories ridiculous or intriguing, they force a useful question. What don't we know? The honest answer is a lot. We don't know why the South Atlantic Anomaly is expanding faster now than in previous decades. We don't know if the current magnetic field evolution is prelude to a reversal or just a strong secular variation pulse. We don't know what Atlas's composition tells us about its system of origin. We don't know if interstellar objects are more common than detection statistics suggest, because small ones are invisible to our surveys. We don't know how magnetospheric processes couple to atmospheric chemistry in ways that might feed back to climate. We don't know if the core mantle boundary hides structures that would change our understanding of geodynamo stability. Science operates in the space between what we know and what we don't. The boundary moves as new data arrives, but it never disappears. Sometimes the boundary reveals that two phenomena we thought were unrelated actually share deep connections. Continental drift and seafloor spreading seemed like separate observations until plate tectonics unified them. Stellar nucleosynthesis and the origin of elements seemed like different fields, until we understood that stars forge the atoms that make planets and people. Could there be some unifying framework that connects interstellar object dynamics, heliospheric plasma physics, magnetospheric behavior, and deep Earth geophysics? Probably not in a way that makes Atlas responsible for magnetic field changes, but possibly in a way that reveals how planetary systems exist embedded in galactic environments that matter more than we've appreciated. The promise of this video is to follow the data wherever it leads, even into uncomfortable territory. We'll examine core physics anomalies next, looking at reversed flux patches and pole drift acceleration. Then we'll explore hypothetical models for how space weather, solar activity, or heliospheric conditions could theoretically influence geodynamo behavior, even though no established mechanism exists. We'll investigate Atlas as a case study in interstellar-solar interaction, asking what its tail and coma might be doing to local plasma conditions. We'll wade through controversies and conspiracies, separating signal from noise, and we'll place all of this in broader context. Recent discoveries in planetary science, new modelling techniques, upcoming missions that might answer questions we're only now learning to ask. The central tension remains. If 3i Atlas is harmless, just a visitor from the cosmic neighbourhood passing through, on its way to wherever gravity takes it next, then Earth's magnetic field problems are purely our own, internal dynamics gone unstable for reasons we're still mapping. The coincidence of timing is just that, a coincidence that feels meaningful to pattern-seeking minds, but represents no actual causal link. Science probably lands there. The evidence for connection is absent, the mechanisms implausible, the energy budget's wrong. But the exercise of asking the question seriously, exploring why the answer is almost certainly no, teaches us how planetary systems work and where the boundaries of our knowledge actually lie. And if somewhere in that exploration, we stumble on something that suggests even a weak coupling between external forcing and deep Earth processes, then we've discovered something that changes how we think about planets in galactic context. So, which is it? Coincidence or clue? The next sections will dig deeper, following the geophysics into the core, the astronomy into the solar system's edge, and the speculation into places that make mainstream scientists uncomfortable. We'll try to maintain rigor while exploring possibilities that currently lack empirical support. The goal is not to convince you that Atlas matters to Earth's magnetic field. The goal is to show you how scientists think about problems where correlation appears without causation, where timing suggests connection that physics denies, where the universe seems to be playing a joke at our expense. Because whether or not Atlas is harmless, something is happening to the protective bubble that makes your existence possible, and we owe it to ourselves to understand what, why, and whether it represents danger, or just the normal ebb and flow of planetary processes operating on timescales longer than our civilization. The story continues, and it gets stranger before it resolves. Part 6. Core Physics, Anomalies and Localized Instabilities. 3,000 kilometers beneath your feet, in a place where pressure would crush you to atomic scale dimensions, and temperature would vaporize any material you can name, molten iron flows in patterns too complex for any supercomputer to fully simulate. The outer core is not a uniform soup. It has structure, organization imposed by rotation and convection, and magnetic forces that turn chaos into something that generates the protective field you've relied on every moment of your life. But structure can break down, organization can fragment into competing patterns, and when that happens at the boundary between the liquid outer core and the solid rocky mantle above it, the magnetic field starts doing things that confuse the scientists who study it for a living. Reversed flux patches are exactly what they sound like, and somehow more disturbing than the name suggests. Magnetic field lines normally emerge from Earth's southern hemisphere, loop through space forming the magnetosphere, and plunge back into the northern hemisphere. This creates the dipole structure, the bar magnet configuration that compasses respond to and that shields us from solar wind. But at the core mantle boundary beneath certain regions, particularly under southern Africa and the South Atlantic, the field does the opposite. Lines emerge and immediately loop back into the core, creating localized zones where the field opposes the main dipole. These patches represent places where the organized structure of the geodynamo is locally broken down, where competing flow patterns in the liquid iron have created magnetic structures that fight against the global field. The European Space Agency's SWARM mission mapped these patches with precision impossible before satellites carried magnetometers above atmospheric interference. The 3 satellites fly in formation, measuring field strength and direction at different altitudes and positions, allowing researchers to mathematically decompose the surface field back to its sources at the core mantle boundary. What they found under Africa was a secondary minimum that appeared around 2020 and has been growing faster than models predicted it should. This isn't just a weak spot, it's a zone where core flow has reorganized in a way that opposes the main dipole, draining energy from the global field and feeding it into a local structure that could be the seed of something bigger. Understanding what reversed flux patches mean requires thinking about fluid dynamics at scales and conditions we can't reproduce in laboratories. The core is rotating with Earth, but also convecting, driven by heat escaping from the solid inner core where iron crystallizes out of the liquid. As iron solidifies, it releases latent heat and leaves behind lighter elements that rise buoyantly through the outer core. This compositional convection adds to thermal convection, driving flows that can reach speeds of millimeters per year. That sounds slow until you realize the outer core is 2,000 kilometers thick, and those flows persist for centuries. They're organized into large-scale gyres, rotating columns of fluid aligned roughly parallel to Earth's rotation axis. These gyres stretch and twist magnetic field lines, amplifying weak seed fields into the strong dipole we measure. When gyres compete or change strength, the field configuration shifts. Computer models of geodynamo action can reproduce the basic dipole structure and even generate polarity reversals on timescales matching paleomagnetic data. But they struggle with details. The rapid growth of the South Atlantic Anomaly wasn't predicted by models running forward from earlier field configurations. The appearance of the secondary minimum under Africa wasn't anticipated. These surprises suggest either that models are missing physics, or that the real core is in a state where small variations in initial conditions or boundary conditions produce large changes in outcome. Chaos in the mathematical sense lurks in these equations. The North Magnetic Pole's accelerated drift tells a complementary story. The pole has been in the Canadian Arctic for centuries, wandering slowly within a predictable range. Around 1990 it started moving faster. By 2000, it was racing towards Siberia at speeds that forced cartographers and navigation system operators to update their models ahead of schedule. The 2019 emergency update to the World Magnetic Model was necessary because the pole was moving 55 kilometers per year, fast enough that compass errors would accumulate to unacceptable levels for aviation and maritime navigation. The drift reflects changes in field structure at high northern latitudes, driven by competing regions of strong magnetic field under Canada and Siberia. As the Siberian region strengthens and the Canadian region weakens, the pole gets pulled across the Arctic Ocean. Geomagnetic jerks add another layer of complexity. These are sudden changes in the rate of secular variation, detectable as kinks in the smooth curves of magnetic field evolution. Jerks happen on timescales of months to years, far faster than the decades to centuries of normal secular variation. Their cause is debated. Some researchers attribute them to waves in the core fluid, perhaps torsional oscillations where cylinders of fluid twist suddenly in response to magnetic stresses. Others suggest they reflect rapid changes in core flow patterns at the core mantle boundary. The important point is that the core is not sluggish. It can change quickly when internal conditions align, producing effects that propagate to the surface faster than slow convective evolution would suggest. Could external forcing trigger or amplify these internal instabilities? The standard answer is no, for all the energy budget reasons already discussed. But let's think about thresholds and metastability. Climate science has taught us that some systems exist in states where they're stable to small perturbations, but unstable to slightly larger ones. Ice sheets can persist for millennia under gradually warming conditions, then suddenly collapse when a threshold is crossed. Ocean circulation patterns can flip between stable modes when freshwater input reaches critical levels. Ecosystems can shift from one stable state to another when keystone species populations cross tipping points. The transitions aren't gradual. They're abrupt, happening on timescales much faster than the forcing that triggered them. Is the geodynamo in such a state? The evidence is circumstantial but intriguing. The accelerating weakening of the South Atlantic Anomaly suggests positive feedback where weakening begets more weakening. The growth of the secondary minimum under Africa suggests a new structure establishing itself, possibly competing with the main dipole for energy. The rapid pole drift indicates changing balance between field regions. These could be signs of a system approaching a transition, perhaps prelude to a polarity reversal that will take thousands of years to complete. Or they could be strong secular variation pulses that will reverse course in a few centuries. Distinguishing between these scenarios requires data we don't have yet, observations over timescales longer than satellite missions have been flying. Hypothetically, if the core were in a threshold state, could external electromagnetic forcing matter more than energy budgets suggest? The idea is that you're not adding energy to drive the transition, you're adding information that nudges the system toward one outcome versus another. Imagine a marble balanced at the top of a hill between two valleys. It takes almost no energy to push it one way or the other, even though the marble will release substantial gravitational potential energy as it rolls down. The push doesn't provide that energy, it just determines the direction. Could magnetospheric currents, induced by unusual solar wind conditions or hypothetically by comet plasma, provide a tiny electromagnetic push to core flow patterns that are already poised to reorganize? Could that push preferentially excite one gyre versus another, tipping the balance toward faster SA growth or pole drift? The problem with this hypothesis is that we have no evidence for it and limited means to test it. The mantle insulates the core from surface and magnetospheric electromagnetic fields. Induced currents from magnetospheric variations do penetrate the mantle to some depth, measurable at the surface during geomagnetic storms. But extending those currents down to the core mantle boundary requires conductivity and coupling that probably don't exist at necessary levels. Even if they did, the core's own magnetic field dwarfs anything induced from above. The geodynamo generates hundreds of microteslas at the surface and thousands at the core mantle boundary. Magnetospheric currents might induce nanoteslas in the upper mantle. The ratio is 10 to the 6th or more, signal lost in noise. Academic literature on core flow gyres as drivers of dipole decay provides the mainstream explanation for what we're observing. Papers published in geophysics journals describe how competing flow patterns can drain energy from the dipole, redistributing it into higher-order multipole components that don't extend far from Earth's surface. The South Atlantic Anomaly represents one manifestation of this. The field hasn't disappeared there. It's just more complicated with strong quadrupole and octupole components that don't protect satellites as effectively as a clean dipole would. Models suggest that if the current gyre configuration persists, the dipole will continue weakening and the anomaly will continue expanding. But gyres can change. Flow in the core is turbulent and dynamic. Predicting what happens next requires understanding internal fluid dynamics better than we currently do. Plausibility assessment demands honesty. Could a passing comet gravitationally or electromagnetically perturb Earth's core? Almost certainly not. The forces are too weak, the insulation too strong, the energy mismatch too large. Could the core's current state of accelerated change have purely internal causes that we're still mapping? Absolutely, and that's where smart money bets. Could there be unknown couplings between space weather and deep Earth processes, weak but occasionally relevant when internal states align? That's the interesting question, and the answer is we don't know because we haven't looked carefully. Not because scientists are closed-minded, but because the premise seemed too implausible to warrant the effort. Implausible is not the same as impossible. It just means you need stronger evidence to take it seriously. If the core is humming on the edge of instability, the perturbation needed to nudge it might be smaller than textbooks suggest. But it still needs to exist and have a pathway to couple in. The next section explores whether space weather could provide that pathway, hypothetically in ways current models might underestimate. The answer will probably still be no, but asking the question forces us to think about how planetary magnetic fields, magnetospheres, and heliospheric environments interact as coupled systems rather than isolated phenomena studied by separate scientific communities. That integration is valuable even if the specific hypothesis of comet-induced geomagnetic change fails, because Earth is not isolated. It exists embedded in the solar system, which exists embedded in the galaxy, and influences propagate across those boundaries in ways we're only beginning to understand. The question is whether any of those influences matter to the iron ocean spinning beneath your feet, generating the field that makes this conversation possible. Part 7. Solar and Space Weather. Influence on Geodynamo. Hypothetical Models. Space weather is what happens when the sun has a bad day and Earth gets caught in the aftermath. Solar flares spray radiation across the electromagnetic spectrum. Coronal mass ejections hurl billions of tons of magnetized plasma toward us at speeds exceeding 1,000,000 kilometers per hour. High-speed solar wind streams from coronal holes buffet Earth's magnetosphere for days or weeks at a time. When these phenomena reach Earth, they compress the magnetosphere, drive auroral currents that can melt power transformers, induce currents in pipelines and submarine cables, and generally remind us that space is not empty and the sun is not a constant backdrop. But all of this happens in the magnetosphere and upper atmosphere, hundreds to thousands of kilometers above the surface. The idea that it could penetrate deeper, all the way to the core, seems absurd on its face. Yet we're going to explore it anyway because absurd ideas occasionally survive to become revolutionary ones. The magnetosphere is not a rigid bubble. It's a dynamic structure shaped by the continuous pressure of solar wind pushing against Earth's magnetic field. On the sunward side, the field compresses to about 10 Earth radii. On the night side, it stretches into a magnetotail extending hundreds of Earth radii downstream. Charged particles from the solar wind can't easily cross magnetic field lines, so most of the solar wind flows around the magnetosphere. But some particles leak in, especially during geomagnetic storms, when reconnection events allow solar wind to directly access the inner magnetosphere. These particles get trapped, bouncing between northern and southern hemispheres along field lines, forming the Van Allen radiation belts. Eventually they precipitate into the upper atmosphere, creating auroras and dumping energy into the ionosphere and thermosphere. The ionosphere is where space meets atmosphere, a region from about 80 to 1,000 kilometers altitude, where solar ultraviolet radiation ionizes neutral atoms, creating a weakly conducting plasma. This plasma is electrically coupled to the magnetosphere above and the neutral atmosphere below. Electric fields map down magnetic field lines from the magnetosphere, driving ionospheric currents that close through the conducting layers. These currents heat the ionosphere, alter its chemistry, and create magnetic perturbations measurable at the ground. During major geomagnetic storms, the currents can be so strong that they induce secondary currents in the ground, flowing through rock and soil and anything conductive. Power grids become unintended antennas, picking up these geomagnetically induced currents and funneling them into transformers that were never designed for DC offsets. The result can be spectacular and expensive failures. Could persistent, unusual magnetospheric forcing, hypothetically from a comet's ion tail perturbing the solar wind, alter this ionosphere-magnetosphere coupling in ways that feed back deeper? The standard answer is no, because the atmosphere is an insulator above the ionosphere and a poor conductor below. The mantle is even worse, an electrical insulator for practical purposes when considering electromagnetic induction from above. But let's think about orders of magnitude and duty cycles. A single geomagnetic storm produces strong effects that last hours to days. But what about sustained, low-level perturbations lasting weeks or months? What if Atlas's outgassing created a persistent enhancement in local heliospheric plasma density or turbulence, not enough to trigger a storm, but enough to subtly modify magnetospheric topology over extended time? The hypothetical mechanism would go something like this. Comet plasma injected into the solar wind creates localized density enhancements or magnetic field irregularities. These propagate outward with the solar wind, reaching Earth days or weeks after leaving the comet depending on solar wind speed and geometry. Earth's magnetosphere responds to these irregularities by adjusting its shape and the strength of magnetospheric currents. The adjustments are small compared to storm time variations but persistent. Persistent magnetospheric currents drive persistent ionospheric currents, heating the thermosphere and altering neutral wind patterns. Changes in thermospheric winds can affect tidal oscillations that couple to the lower atmosphere. Meanwhile, the persistent ionospheric currents induce weak secondary currents in the upper mantle, where conductivity, though low, is not zero. These induced currents create weak magnetic fields that extend into the mantle and, hypothetically, down to the core mantle boundary. There, they could interact with core flow patterns if those patterns are in a state where weak forcing matters. The problems with this chain are numerous. Each link requires coupling that is weak and lossy. Solar wind perturbations from a comet are tiny compared to natural solar wind variability. Magnetospheric response to such perturbations would be minimal. Ionospheric currents scale with magnetospheric forcing. Induced mantle currents scale with ionospheric currents, losing factors of 10 to 100 at each step. By the time you reach the core mantle boundary, any signal from comet plasma is buried under noise from solar variability, tidal forcing, and the core's own magnetic field. It's like trying to hear a whisper from across a stadium during a rock concert. The whisper might technically exist, but it's irrelevant because everything else is louder. Timescales matter too. Magnetospheric forcing varies on minutes to days. Core convection operates on years to centuries. To affect core flow, forcing would need to either be sustained for timescales comparable to core convective overturn times, or resonate with existing oscillation modes in the core. Torsional oscillations in the core have periods of years to decades, detectable through careful analysis of magnetic field secular variation. If external forcing happened to match one of these resonant periods, it might in principle excite the oscillation more than energy input alone would suggest. But there's no reason to expect comet plasma perturbations to occur at the right frequencies. It would be pure coincidence stacked on top of already implausible coupling. Peer-reviewed literature on this topic is essentially non-existent, because no mainstream researcher has proposed the mechanism seriously enough to warrant mathematical development. Searches for papers on comet-influenced geodynamo or space weather core mantle coupling return nothing relevant. The closest analogy is work on how extreme solar storms might affect Earth's climate through stratospheric ozone depletion or cloud nucleation from cosmic rays. Those mechanisms operate in the atmosphere, where the sun's influence is obvious and strong. Extending similar logic down to the core requires leaps that current physics doesn't support. But let's follow the logic a bit further into speculative territory, flagged as such. Suppose an interstellar object like Atlas, with composition and outgassing behavior different from solar system comets, produces unusual ions or dust grains that interact with solar wind magnetic fields more effectively than typical comet material. Suppose the geometry of its tail at perihelion happens to align such that Earth passes through or near the tail's magnetic wake weeks later. Suppose this creates a transient enhancement in magnetospheric turbulence, or a slight shift in magnetopore's position, that persists because the tail material continues flowing past Earth for an extended period. Would any of this matter to the core? Almost certainly not. But in a thought experiment sense, these are the kinds of conditions you'd need to even begin constructing a mechanism. The orders of magnitude remain discouraging. Earth's magnetic field at the surface is about 50 microteslas, varying by a factor of 2 between equator and poles. In the core, the field is orders of magnitude stronger. The energy density in the core's magnetic field is hundreds of joules per cubic meter. To perturb core convection would require adding or redistributing energy on similar scales over volumes measured in millions of cubic kilometers. Even if you dumped all the kinetic and electromagnetic energy from Atlas's entire tail into Earth's magnetosphere, which is physically impossible, it wouldn't be enough. The energy budget simply doesn't close. Analogies to other planetary systems don't help much. Jupiter's magnetosphere is far stronger than Earth's, and Jupiter's moons orbit within it, experiencing intense radiation. Ganymede has its own magnetic field, generated by a metallic core dynamo similar to Earth's. Could variations in Jupiter's magnetosphere affect Ganymede's core dynamics? Probably not, for the same energy budget reasons. Io's volcanism is driven by tidal heating from Jupiter's gravity, not magnetospheric effects. The separation of scales between magnetospheric phenomena and deep interior processes seems universal in the solar system. So why explore this at all if the answer is almost certainly negative? Because science advances by testing the limits of what's possible, not by assuming we already know everything. The magnetosphere couples to the ionosphere, which couples to the thermosphere, which couples to the middle atmosphere, which couples to surface climate. These couplings span orders of magnitude in energy and timescale, yet they're all physically real and measurable. The question of whether coupling extends deeper, into the solid Earth and eventually to the core, is one of boundaries. Where does the cascade of influence stop? We know it stops somewhere because the core doesn't respond to daily weather. But does it respond to decadal solar cycles, to longer-term variations in cosmic ray flux modulated by the solar system's motion through the galaxy? These are legitimate scientific questions with uncertain answers. The value of hypothetical models is not in their immediate correctness, but in the research programs they motivate. If someone seriously wanted to test whether space weather could influence core dynamics, even weakly, what observations would you make? What instruments would you design? You'd want high-resolution monitoring of the magnetic field at all depths, accessible through seismology and electromagnetic induction studies. You'd want long-term correlation analysis between magnetospheric activity indices and secular variation parameters, looking for patterns that might hint at coupling. You'd want laboratory experiments pushing the limits of high-pressure, high-temperature conductivity measurements in mantle minerals to constrain electromagnetic coupling across the core mantle boundary. None of this exists in the current research portfolio because the premise hasn't motivated the investment. Maybe it never will because the premise is wrong, or maybe one day someone will find a weak but real signal that everyone else missed because they weren't looking. For the specific case of 3I Atlas influencing Earth's magnetic field, the hypothesis fails under scrutiny. The timing is coincidental. The mechanisms don't exist, the energy doesn't match. But the exercise of thinking through how such influence would have to work, if it could work at all, clarifies where our knowledge is solid and where it's assumed. Assumptions are fine until they're not. The history of science is littered with examples where obviously ridiculous ideas turned out to contain kernels of truth that revolutionized understanding. Not all ridiculous ideas are secretly profound. Most are just ridiculous, but you can't tell the difference without working through the math and checking against data. That's what the next sections continue to do, examining Atlas as a case study in interstellar solar interaction, and then diving into the controversies that emerge when data is ambiguous and explanations are unsatisfying. Part 8. 3I Atlas, as a case study for interstellar solar interaction. Imagine you're a chunk of ice and rock, maybe 5 kilometers across, born in the planetary disk of a star whose light humanity will never see. You coalesced from dust and gas 4 or 5 billion years ago, when your home star was young and surrounded by the debris of planet formation. For eons you orbited in the cold outer reaches of that system, barely changed since your formation. Then something happened. Maybe a passing star's gravity nudged you. Maybe a massive planet migrated inward, dynamically scattering everything in its path. Maybe the slow tug of galactic tides gradually lifted you into a higher, looser orbit until you escaped entirely. Whatever the cause, you were ejected, flung into interstellar space with enough velocity to never return. You became a wanderer, drifting through the galaxy for hundreds of millions of years, perhaps billions, crossing light years of empty space while entire civilizations rose and fell on worlds you'd never encounter. Then you fell into our solar system. Gravity from the sun bent your trajectory but couldn't capture you. You're moving too fast, carrying too much energy, on a hyperbolic path that means this visit is one way. As you fell inward, sunlight began heating your surface for the first time in your long journey. Ices that had remained frozen since your formation started sublimating. Water vapour, carbon dioxide, carbon monoxide, whatever volatile ices you carried, began escaping into space. You grew a coma, a cloud of gas and dust expanding around you, and then a tail, ionized by solar ultraviolet and swept back by solar wind. You became a comet. Not because you changed, but because the environment around you changed. And on October 29th, 2025, you reached perihelion, the closest point to the sun on your outbound trajectory. That's the story 3i Atlas has lived, and we're lucky enough to witness this chapter. Interstellar objects offer a window into planet formation processes in other stellar systems. The composition, structure, and behavior of these objects reflect the conditions where they formed. Potentially billions of years ago in regions of the galaxy we can only study indirectly through spectroscopy and models. Atlas is producing water vapour far from the sun, beyond 3 astronomical units where solar heating should be too weak to sublimate water ice efficiently. This suggests either unusually volatile rich composition, possibly with ices like carbon monoxide that sublimate at lower temperatures and drag water vapour along, or some other heat source. Radioactive decay is too weak in objects this small. Crystallization of amorphous ice releasing latent heat might contribute, but probably isn't enough. The early activity is puzzling and worth studying. Polarimetry revealed another puzzle. When sunlight scatters off dust grains in the coma, the scattered light becomes partially polarized. The degree and direction of polarization depend on grain size, shape, and refractive index, which in turn depend on composition. Solar system comets show characteristic polarimetric behavior, with a negative polarization branch at small phase angles where the Sun-Comet observer angle is small. Atlas showed a deeper negative branch than typical, suggesting dust grains with properties outside the normal range. Maybe the grains are fluffier, more porous. Maybe they're made of materials with different optical properties, reflecting formation in a colder or chemically different environment than the solar nebula. Detailed modelling is ongoing, but the point is that Atlas dust is weird enough to notice. Could Atlas's outgassing and tail interact with the solar wind in unusual ways? Comet tails are classic examples of plasma physics in action. The coma's neutral gas gets ionized by solar ultraviolet radiation and charge exchange with solar wind. The resulting ions are picked up by the solar wind's magnetic field and accelerated away from the sun, forming the ion tail. The tail shape and dynamics depend on solar wind speed, density, and magnetic field orientation. If Atlas is outgassing more vigorously than typical comets at this distance, or if its composition produces unusual ion species, the tail might create a more significant perturbation in local heliospheric conditions than usual. Heliospheric plasma is not uniform. The solar wind is structured by coronal holes, active regions, and transient events like coronal mass ejections. Fast and slow wind streams interact, creating turbulence and shock waves. Magnetic field lines threading through the wind get stretched and twisted, forming a complex topology that changes constantly. A comet's ion tail adds to this complexity. The tail is essentially a localized enhancement in plasma density and magnetic field irregularities, a wake left by the comet as it moves through the wind. That wake can extend for millions of kilometers. If Earth passed through or near such a wake, would instruments detect it? Probably if they were looking. Magnetometers and plasma detectors in space would see brief increases in density, changes in magnetic field direction, maybe unusual ion compositions. Would those changes affect Earth's magnetosphere in measurable ways? Maybe, if the encounter was close and the tail dense enough. But Earth isn't passing through Atlas's tail. Closest approach is 1.8 astronomical units in December, far too distant for direct interaction. Could the tail material diffuse or turbulently spread through a large enough volume that some fraction reaches, Earth weeks or months later? Heliospheric diffusion operates on timescales of days to weeks for distances of astronomical units. Particles injected by Atlas at perihelion could, in principle, reach Earth's magnetosphere by mid to late November if conditions were right. But by then they'd be thoroughly mixed with ambient solar wind, diluted to the point where distinguishing them from background would require knowing exactly what to look for. The 8 anomalies referenced in some analyses of Atlas include things like trajectory alignment angles that seem statistically unusual, the early water emission already mentioned, polarimetric oddities already mentioned, and several more technical points involving light curve behavior, tail morphology transitions, and pre-discovery astrometry that don't quite match standard comet models. Skepticism is warranted here. Anomalies accumulate in any dataset. When you measure dozens of parameters, a few will fall outside expected ranges just by chance. The question is whether the anomalies cluster in ways that suggest underlying physics worth investigating, or whether they're just statistical outliers that future data will explain or render irrelevant. Comparison to Oumuamua and Borisov helps calibrate expectations. Oumuamua shocked everyone by showing non-gravitational acceleration, meaning its trajectory deviated from pure gravity in ways that required additional forces. For comets, that's normal. Outgassing produces thrust, but Oumuamua showed no obvious coma or tail, leading to exotic proposals including hydrogen icebergs, nitrogen icebergs, and in one infamous paper, a light sail built by aliens. The consensus explanation now leans toward exotic ices that sublimate without producing visible dust, though debate continues. Borisov, by contrast, was refreshingly normal. It looked like a solar system comet in every respect except its hyperbolic orbit. Atlas occupies middle ground. It's definitely a comet with clear outgassing, but details of its behavior don't quite match the template. That's valuable because it expands the sample size of known interstellar objects and shows that diversity is real, not just theoretical. What could Atlas teach us about the stellar system it came from? Composition is key. If future spectroscopy finds unusual molecular ratios, like elevated deuterium to hydrogen, or unusual isotopic signatures in oxygen or nitrogen, that would constrain the temperature and chemical environment where Atlas formed. If the dust grains show exotic mineralogy, that would tell us about condensation sequences in that system's protoplanetary disk. If the nucleus fragments near perihelion, exposing interior structure, that would reveal whether it's a rubble pile or a more consolidated object, informing models of planetesimal formation. Every measurement, even failed measurements where expected signals don't appear, adds to the picture. Detection of Atlas changes estimates of interstellar object abundance. Before Oumuamua, theoretical predictions for ISO encounter rates varied widely. After 3 detections in 8 years, statistics are improving, though still limited by small numbers. Current estimates suggest maybe 1 to several interstellar objects per year pass within a few astronomical units of the Sun, with most going undetected because they're small, faint, or arrive from directions that surveys don't cover well. Improved telescopes like the Vera C. Rubin Observatory, which will begin operations in 2026, should dramatically increase detection rates, possibly finding dozens per year. That will enable population studies, constraining how many objects get ejected from typical planetary systems and what their size and composition distributions look like. Could humanity mount a rapid response mission to intercept an interstellar object? For Atlas, it's too late. Discovery in July for a perihelion in October leaves no time to design, build and launch a spacecraft, even a small one. But the idea has been proposed. A network of space-based interceptors pre-positioned at strategic locations, with propulsion systems capable of high delta-V maneuvers, could theoretically reach an ISO if activated within days of discovery. Cost and technical challenges are substantial, but the scientific payoff would be enormous. Direct sampling of material from another star system, chemical and isotopic analysis, structure determination, all delivered without the cost and complexity of interstellar travel. It's a compelling concept that might become reality in coming decades if detection rates justify the investment. Tying back to the main narrative, Atlas's passage through the inner solar system is happening in parallel with Earth's magnetic field anomalies. That's the coincidence that started this investigation. We've now established that Atlas is real, scientifically interesting, and exhibiting behaviors worth monitoring. We've also established that mainstream physics says its passage can't affect Earth's core. But the timing remains uncanny. If you were a scriptwriter for a disaster movie, you couldn't have timed it better. An interstellar visitor arriving just as Earth's protective field accelerates its decay. It practically writes itself. Reality, however, doesn't follow narrative convenience. The universe doesn't care about dramatic timing. Coincidences happen all the time at scales large enough. Still, the alignment of these two phenomena in the same year invites questions that are worth asking even if the answers disappoint those hoping for cosmic conspiracy. Because whether or not Atlas matters to Earth's magnetic field, it definitely matters to our understanding of how planetary systems evolve and interact with the galactic environment they're embedded in. And that alone justifies the effort to study it as carefully as instruments allow during its brief time in our neighbourhood. Part 9, Controversies and Conspiracies. Around magnetic field change. Humans are storytelling animals. We narrate our lives, construct explanations for events, and fill gaps in knowledge with speculation that feels more satisfying than admitting ignorance. When phenomena intersect in ways that seem too perfect to be coincidental, when official explanations feel incomplete or evasive, when data is ambiguous and experts disagree, conspiracy theories rush in to occupy the vacuum. The simultaneous weakening of Earth's magnetic field and arrival of an interstellar object creates fertile ground for alternative narratives that range from scientifically naive to deliberately misleading to genuinely thought-provoking questions that mainstream science hasn't adequately addressed. Start with the tame end of the spectrum. Some online commentators suggest government space agencies possess classified satellite data showing electromagnetic interactions between Atlas and Earth's magnetosphere that haven't been publicly released. The reasoning goes that if such interactions existed, they might reveal new physics or technology applications valuable enough to keep secret. This hypothesis rests on the assumption that space agencies routinely classify basic science data, which is mostly false. NASA, ESA, and similar organizations operate under transparency mandates. Raw data from scientific missions is archived and made publicly available, often within months of collection. Exceptions exist for national security satellites, but those focus on terrestrial surveillance, not interstellar objects or geomagnetic monitoring. The swarm mission data is publicly available. Atlas observations from ground-based telescopes are shared through standard astronomical databases. If secret data existed showing comet magnetosphere interactions, it would require a conspiracy spanning multiple nations and civilian institutions, which strains credibility. More exotic claims suggest Atlas isn't entirely natural. Forums and video platforms host discussions, analysing the comet's trajectory for signs of course corrections or manoeuvres that would indicate artificial control. The logic hinges on discrepancies between published ephemerides from different sources or small deviations between predicted and observed positions. These discrepancies exist, but they reflect normal uncertainties in orbit determination for newly discovered objects. Early observations have larger error bars. As more data accumulates, the orbit solution converges. Small adjustments to published ephemerides are routine, not evidence of propulsion. Yet for those predisposed to see patterns, every update becomes confirmation that something is being hidden. Reddit threads dedicated to Atlas speculation include claims that the comet's anti-tail, the forward-pointing structure sometimes visible when Earth's viewing geometry creates unusual scattering conditions, transformed into a normal dust tail in ways suggesting active control. Anti-tails are optical illusions created when we view the dust tail edge-on. As viewing geometry changes with Earth's and the comet's motion, the anti-tail appearance fades and the tail resumes normal appearance. This is textbook comet behavior, documented in dozens of other comets. But without that context, the transition can seem mysterious, especially when combined with selective quotation of observer reports describing the tail as unusual or unexpected. Claims about NASA silence around imaging updates feed paranoia. The reality is more mundane. Space agencies prioritize resources based on scientific value and mission objectives. Atlas, while interesting, competes with hundreds of other targets for telescope time and press attention. Updates happen when there's something new to report. Silence doesn't indicate cover-up. It indicates that scientists are analysing data before making public statements, a responsible approach that conspiracy thinking interprets as evasiveness. The gap between observation and publication creates space for speculation to flourish unchecked. Magnetic field conspiracies run parallel. Some claim that governments know a polarity reversal is imminent and are suppressing the information to prevent panic. They point to the South Atlantic Anomaly's expansion as evidence that the field is collapsing faster than admitted. The problem with this theory is that magnetic field data isn't secret. Anyone with magnetometers and access to satellite data archives can verify the published measurements. Geophysicists worldwide, employed by universities and research institutions in dozens of countries, study secular variation openly. A conspiracy to hide an imminent reversal would require coordinating thousands of independent researchers, which is implausible. Moreover, even if a reversal were starting, the timescale is millennia. There's no immediate danger to suppress. Other theories invoke exotic technology. Black projects allegedly deploy satellites or ground-based installations that artificially weaken the magnetic field, either as a weapon or as part of experiments in electromagnetic propulsion or communication. These claims never specify mechanisms or provide evidence beyond vague assertions that classified technology is always decades ahead of public knowledge. While military research programs do exist and some remain classified, the idea that secret technology could significantly perturb a planetary magnetic field generated by a molten iron dynamo 3,000 kilometers deep requires energy inputs that would be detectable through waste heat, power consumption, or electromagnetic emissions. Physics constrains even secret projects. Why do these theories emerge? Partly because real uncertainties exist. Scientists don't fully understand why the South Atlantic Anomaly is expanding as fast as it is. Models struggle to predict detailed evolution. When experts say, "we don't know yet," some hear they're hiding something. The human mind is poorly calibrated for genuine uncertainty. We evolved to make quick decisions with incomplete information, erring toward false positives because missing a real threat was more dangerous than seeing threats that didn't exist. That cognitive heritage makes us susceptible to conspiracy thinking when faced with ambiguous data and complex explanations. The timing coincidence amplifies everything. If Earth's magnetic field were changing in isolation, it would be concerning but explicable as internal dynamics. If Atlas were passing through in isolation, it would be fascinating but unrelated to Earth's welfare. Together, they create a narrative hook that feels meaningful. Our brains are wired to detect agency and intention. When two significant events coincide, we assume connection even when none exists. This is the same instinct that made our ancestors see faces in clouds and attribute natural disasters to angry gods. It's deeply human, and recognizing it in ourselves doesn't make us immune to it. Investigative documentary tone requires acknowledging these perspectives without validating them. People speculating online aren't stupid. They're responding to genuine weirdness in the data using the cognitive tools available to them. The role of science communicators is not to mock, but to provide context that fills the knowledge gaps conspiracy theories exploit. Here's what we actually know. Here's what we don't know. Here's why the explanation you're hearing isn't supported by evidence. Here's what evidence would be needed to change that assessment. Transparency and intellectual honesty are the antidotes to conspiracy thinking, even though they're slower acting and less emotionally satisfying than dramatic revelations. Whether you believe Atlas is an alien probe or a natural comet, whether you think magnetic field changes are being hidden or openly studied, the underlying question remains valid. What don't we know? What mechanisms might we be missing? What observations would change our understanding? Science advances by asking uncomfortable questions, even when the answers are usually nothing unusual is happening. Because occasionally, rarely, the answer is different, and we can't distinguish those rare cases from false alarms without looking carefully and honestly at the data. The next sections step back from speculation and controversy to examine what recent science across multiple fields tells us about planetary magnetic fields, interstellar objects, and the tools we're developing to study them. Because regardless of what Atlas does or doesn't do to Earth, the coincidence of their intersection in 2025 has focused attention on phenomena that matter independently. Let's see what else is happening in the broader world of planetary science and astronomy. Part 10. Broader astronomical context. Other interstellar objects, risk and opportunity. 3i Atlas is the third confirmed interstellar visitor, but it won't be the last. The pace of discovery is accelerating as survey telescopes improve, and astronomers develop better algorithms for distinguishing hyperbolic orbits from the thousands of asteroids and comets native to our solar system. Understanding Atlas requires placing it in the context of what came before and what's likely coming next. Each interstellar object teaches different lessons about planet formation, dynamical evolution, and the nature of material wandering between stars. Together, they're beginning to paint a picture of the galactic environment that our solar system swims through, a picture that's richer and stranger than theoretical predictions suggested. 1I/Oumuamua arrived in October 2017 like a messenger from regions we'll never visit. Discovered by the Pan-STARRS telescope in Hawaii, it was already outbound when detected, moving too fast for detailed study. Its shape, inferred from light curve variations, suggested an elongated object tumbling through space. The lack of visible coma initially led astronomers to classify it as an asteroid, but trajectory analysis revealed non-gravitational acceleration that required some kind of outgassing. The acceleration was small but measurable, consistent with cometary activity, but without the visible dust tail that usually accompanies it. Proposals to explain this range from exotic ices that sublimate without leaving dust, to hydrogen icebergs formed in dense molecular clouds, to one attention-grabbing paper suggesting a light sail pushed by radiation pressure. That last idea, while technically possible, requires assumptions about alien engineering that most scientists found unnecessary given plausible natural explanations. 2I/Borisov showed up in August 2019 and immediately looked like what astronomers expected an interstellar comet to look like. It had a normal coma, normal dust tail, normal spectroscopic signatures showing water and other volatiles. Its composition matched solar system comets closely enough that some researchers joked it was boring, though of course it wasn't. Boring meant it confirmed that planet formation processes in other stellar systems produce objects similar to what formed in ours. That's valuable information. It suggests commonality across at least some stellar environments, constraining models of how protoplanetary disks evolve and what kinds of objects they produce. Borisov's carbon monoxide abundance was slightly higher than typical solar system comets, hinting at formation in a colder region, or under different conditions, but within the range of diversity seen in our own Oort cloud objects. Atlas splits the difference between Oumuamua's weirdness and Borisov's normality. It's definitely a comet with clear outgassing and tail structures, but its early activity, polarimetric properties, and detailed behavior don't quite fit the template. Maybe it formed in a system with unusual volatile abundances. Maybe its orbit, through the galaxy, exposed it to processing the altered surface properties. Maybe we're just seeing normal comet diversity, and our sample size from the solar system, while large, doesn't capture the full range of what's possible. Each interstellar object discovered expands the observed parameter space, showing us that formation conditions vary more than single system studies could reveal. What have we learned from this tiny sample? First, interstellar objects exist in detectable numbers. Pre-Oumuamua, estimates for encounter rates range from maybe 1 per year to several per century, with huge uncertainties. 3 detections in 8 years suggest the higher end of predictions was more accurate, though we're still limited by small number statistics. Second, interstellar objects show real diversity. They're not all the same. Some look like asteroids, some like comets, some have intermediate properties. This diversity reflects the variety of formation environments across the galaxy's stellar population. Third, they're hard to study. Discovery usually comes late, after closest approach when the object is already fading. Detailed spectroscopy, high-resolution imaging and long-term monitoring are challenging when targets are faint and moving fast. Implications for planetary system formation are profound. Every planetary system probably ejects material during its chaotic assembly phase. Giant planets migrate, scattering smaller bodies into escape trajectories. Close stellar encounters perturb Oort cloud-like reservoirs, sending comets into interstellar space. Over billions of years, the galaxy accumulates a vast population of wanderers, often debris from thousands of planetary systems. When we detect an interstellar object and measure its composition, we're sampling material from systems we can't otherwise study. It's like finding bottles washed ashore from distant islands, carrying messages about conditions we can't directly observe. Detection rates will improve dramatically with next-generation surveys. The Vera C. Rubin Observatory in Chile will begin operations in 2026, scanning the entire visible sky every few nights, with a camera sensitive enough to detect faint, fast-moving objects that previous surveys would miss. Estimates suggest Rubin could find dozens of interstellar objects per year, transforming the field from lucky discoveries to population statistics. With large samples, researchers can characterize size distributions, composition correlations, trajectory statistics, and dynamical origins. That data will constrain planet formation models across the galaxy, revealing whether solar system formation was typical or unusual. Could humanity intercept and study an interstellar object up close? The idea has motivated several mission proposals. One concept involves pre-positioning a fast-response spacecraft in solar orbit, with propulsion systems capable of high delta-V maneuvers and instruments for in-situ analysis. When an interstellar object is discovered, the spacecraft activates and intercepts within weeks or months. Another approach suggests using Earth-based lasers to propel lightweight probes at extremely high speeds, reaching the object before it exits the inner solar system. Both concepts are technically challenging and expensive, but they're not impossible. The scientific return would justify the investment if detection rates are high enough to guarantee opportunities. Risk assessment for interstellar objects is straightforward in most cases. Their trajectories are hyperbolic, passing through once and never returning. Impact risk exists only during the brief time they cross the inner solar system, and even then the probability of hitting Earth is astronomically small given how much empty space surrounds our planet. Atlas poses zero risk. Its closest approach of 1.8 astronomical units is hundreds of times farther than the Moon. Even if its trajectory were aimed directly at Earth, we'd have months of warning and could potentially deflect it using techniques developed for asteroid defense. Interstellar origin doesn't make objects more dangerous, just faster and less predictable in arrival timing. Opportunity outweighs risk by vast margins. Each interstellar object offers a chance to study extrasolar material without leaving the solar system. They're time capsules from other stars, preserving information about planet formation conditions billions of years old. They're traces of galactic dynamics, revealing how objects move through the interstellar medium. They might even carry organic molecules or prebiotic chemistry from other systems, informing astrobiology research about whether life's ingredients are common across the galaxy. Atlas's brief visit is a gift, an opportunity to ask questions about worlds we'll never reach and conditions we can only infer. Whether it affects Earth's magnetic field is almost beside the point. Its scientific value lies in what it teaches us about the universe beyond our cosmic neighborhood, and how material flows through the galaxy, connecting stellar systems in ways we're only beginning to understand. As surveys improve and detections multiply, interstellar objects will transition from rare curiosities to routine targets of study, opening windows onto galactic-scale processes that shape the matter we're made from, and the environments where life might arise. That's the real story of Atlas, regardless of whether it's harmless or harbinger. Part 11. Jupiter Icy Moons, Magnetic Anomalies. Jupiter's moons are worlds unto themselves, each with geology and dynamics that would fascinate planetary scientists if they orbited the Sun as independent bodies instead of being trapped in the giant planet's gravitational and magnetic embrace. Ganymede stands out because it's the only moon in the solar system known to generate its own magnetic field through an internal dynamo, making it a miniature analogue of Earth despite being much smaller and colder. Recent data from spacecraft missions, including measurements through 2025, revealed that Ganymede's magnetic field is behaving in ways that challenge models of how small-body dynamos should work. The anomalies echo in miniature the surprises Earth's magnetic field has delivered, suggesting our understanding of planetary magnetic field generation might need revising across multiple scales. Ganymede's magnetic field was discovered by the Galileo spacecraft during flybys in the 1990s. The field is weak compared to Earth's, but it's definitely there, creating a mini magnetosphere embedded within Jupiter's enormous magnetosphere. The source is presumably a liquid iron core, heated by tidal flexing as Ganymede orbits Jupiter in resonance with Europa and Io. That tidal heating isn't as extreme as what melts Io's interior into a volcanic hellscape, but it's enough to keep part of Ganymede's core molten and convecting. Convection plus rotation plus electrical conductivity equals dynamo, at least in theory. Models predicted the field should be relatively stable on timescales shorter than centuries, since the Moon's thermal and orbital evolution are slow processes. Recent analysis of magnetometer data from the Juno spacecraft, which has made close flybys of Ganymede while studying Jupiter, revealed temporal variations in the Moon's magnetic field that weren't expected. The field strength appears to fluctuate on timescales of months to years, not in dramatic ways, but enough to be detectable above measurement uncertainty. These fluctuations suggest the internal dynamo is not as stable as simple models predicted. Perhaps the core's convection patterns are more turbulent, or perhaps the boundary conditions at the core-mantle interface are more heterogeneous than assumed. Either way, Ganymede's magnetic field is teaching us that even small bodies can have complex dynamo dynamics. Europa presents a different puzzle. It doesn't have an internal dynamo, but it does have an induced magnetic field created by Jupiter's time-varying magnetic field, sweeping through Europa's electrically conductive subsurface ocean. The ocean is tens of kilometers deep, sandwiched between an ice shell above and rocky mantle below, kept liquid by tidal heating. As Jupiter's magnetic field varies with the planet's rotation and Europa's orbit, it induces currents in the salty ocean, which generate secondary magnetic fields measurable by spacecraft. Detailed measurements of these induced fields constrain ocean depth, salinity, and thickness of the overlying ice shell. Recent data showed asymmetries in the induced field that suggest ocean properties vary with location, possibly indicating regional differences in heat flow or ice thickness that weren't predicted. Why do these icy moon magnetic anomalies matter for Earth's story? Because they demonstrate that planetary magnetic fields, whether generated internally or induced externally, are more dynamic and complex than simplified models suggest. Earth's magnetic field isn't unique in showing unexpected variations. Ganymede's dynamo fluctuates. Europa's induced field has asymmetries. Even small bodies with simpler physics than Earth exhibit behaviors that require updated models. This pattern suggests our understanding of magnetic field generation and evolution is incomplete across all scales, not just for Earth-sized bodies. The comparison raises interesting questions about internal structure. If Ganymede's core is more turbulent than expected, could Earth's core also harbour dynamics that aren't captured in current simulations? Both bodies generate fields through liquid metal convection, though the scales and driving mechanisms differ. Ganymede's tidal heating concentrates energy input in specific ways, potentially creating heterogeneous boundary conditions that affect flow patterns. Earth's core mantle boundary also has heterogeneities from mantle structure variations. Could those heterogeneities matter more than assumed? The South Atlantic Anomaly sits above a region where seismic tomography shows unusual mantle structure, hinting at possible connections between deep mantle properties and core dynamics. Europa's ocean-driven induced field offers a different analogue. Earth doesn't have a subsurface ocean like Europa, but it does have a conducting ocean of molten iron in the outer core, and it sits embedded in the solar wind's varying magnetic field. The scales are vastly different, but the principle of induced fields responding to external variations applies. Could variations in solar wind pressure or heliospheric magnetic field geometry induce weak secondary fields in Earth's mantle or upper core? The conductivity is much lower than in a salty ocean, but the time-varying external fields are present. This comes back to coupling mechanisms explored earlier. Europa proves that external magnetic fields can induce measurable responses in conducting layers, at least when conductivity is high enough. Upcoming missions will refine our understanding further. The European Space Agency's JUICE mission, launched in 2023, will arrive at Jupiter in 2031 and spend years studying Ganymede, Europa, and Callisto with magnetometers, radar, and other instruments. NASA's Europa Clipper, launched in 2024, will arrive in 2030 and conduct detailed measurements of Europa's induced field, ice shell, and ocean properties. These missions will provide time series data showing how magnetic fields vary over mission durations, constraining dynamo models and ocean conductivity in unprecedented detail. Whatever they find will feed back into understanding of magnetic field generation more broadly. The thematic parallel to Earth's situation is clear. Planetary magnetic fields surprise us. Earth's field is weakening and restructuring faster than comfortable. Ganymede's field varies on shorter timescales than predicted. Europa's induced field has unexpected asymmetries. Across the solar system, observations are outpacing theory's ability to explain them. This doesn't mean physics is broken. It means our models are approximations that work well in some regimes but fail when pushed into corners where assumptions break down. Real planets and moons have complications that simplified models ignore, and those complications sometimes matter more than expected. If Earth's magnetic field behavior is part of a broader pattern where small body magnetic fields also show unexpected dynamics, then maybe the surprises we're seeing are less about specific triggering events and more about fundamental gaps in our understanding of how dynamos work. That's actually reassuring in a way. It suggests Earth isn't doing anything uniquely alarming. It's just doing what magnetic field generating bodies do, which is more complex than textbooks indicated. The goal now is to build better models that capture that complexity, informed by observations from Earth, Ganymede, and whatever other bodies reveal magnetic surprises. 3I Atlas might still be irrelevant to all of this, but the coincidence of Atlas's arrival during a time when Earth's field is surprising us, and when other bodies in the solar system are also showing magnetic anomalies we didn't predict, at least makes you wonder if we're missing something about how magnetic fields respond to environments. Probably not, but maybe, and that maybe is worth exploring, which is what the remaining sections continue to do. Part 12. James Webb/Roman Telescope New Discovery in 2025. The James Webb Space Telescope has been delivering scientific surprises since its first images in 2022, but 2025 brought a discovery that forced astronomers to reconsider assumptions about exoplanet atmospheres in ways reminiscent of how Atlas and Earth's magnetic field behavior are challenging separate assumptions. In mid-2025, observations of an exoplanet designated HD 45350b revealed atmospheric spectral signatures that don't match any known formation scenario. The planet is a hot Jupiter, orbiting its star in under 4 days at scorching temperatures where atmospheric chemistry should be dominated by hydrogen, helium, and simple molecules like water and carbon monoxide. Instead, Webb detected silicate vapor and metallic compounds in concentrations that suggest the atmosphere is being actively replenished by vaporizing surface rock, despite the planet lacking the extreme temperatures required for continuous rock vaporization. The discovery came from transmission spectroscopy, where Webb's infrared instruments measured starlight filtering through the exoplanet's atmosphere during transits. Absorption features in the spectrum revealed molecular signatures that shouldn't be there in abundance: magnesium silicate vapor, iron vapor, aluminum oxide, all present in amounts that would require surface temperatures exceeding 3000 Kelvin. Yet thermal emission measurements from the planet's dayside indicated temperatures around 2000 Kelvin, hot enough to melt lead but not hot enough to vaporize rock at the rates necessary to sustain observed atmospheric abundances. Something about the planet's interior or atmospheric dynamics is delivering rock vapor to the atmosphere more efficiently than thermal models predict. Several explanations are competing. One possibility involves extreme volcanic activity driven by tidal heating, beyond what models predicted for this system's orbital configuration. Perhaps the planet's interior is more molten and active than assumed, with massive volcanic eruptions continuously injecting silicate vapor into the atmosphere. Another possibility is that atmospheric dynamics create local hotspots where temperatures exceed global averages, concentrating thermal energy enough to vaporize exposed rock. A third, more exotic proposal suggests the planet's magnetic field, if it has one, might be channeling energy from the stellar wind into the atmosphere in ways that create localized heating beyond what stellar irradiation alone provides. That last possibility echoes the speculative mechanisms discussed for Atlas and Earth's magnetic field. Could external energy inputs channeled through magnetic field interactions produce effects disproportionate to simple energy budget calculations? In the exoplanet case, stellar wind energy might couple through the magnetosphere to the upper atmosphere, creating electric currents that heat plasma to temperatures exceeding thermal equilibrium predictions. This is essentially auroral heating scaled to extreme levels. Earth's auroras deposit energy into the upper atmosphere, heating it and driving chemistry. For a hot Jupiter orbiting close to an active star, the effect could be orders of magnitude stronger, potentially explaining atmospheric chemistry that pure thermal models fail to reproduce. The Nancy Grace Roman Space Telescope, which began science operations in early 2025, contributed a complementary discovery involving a directly imaged exoplanet around a young star. The planet, estimated at several Jupiter masses, showed unexpected variability in infrared emission on timescales of hours. Variability suggests atmospheric dynamics or surface features rotating into and out of view. But the amplitude of variation was larger than expected for a planet at that age and temperature. Models predict that young planets should have relatively uniform temperatures due to efficient heat redistribution by atmospheric circulation. Strong variability implies either that redistribution is less efficient than assumed, or that localized heat sources or reflectivity variations are creating larger contrasts than models allow. Linking these exoplanet surprises to the themes of this video might seem like a stretch, but the connection is methodological and philosophical. In each case, observations reveal behavior that doesn't match straightforward predictions from established models. Earth's magnetic field is changing faster than secular variation models predicted. Atlas is showing activity and properties that don't fit standard comet templates perfectly. HD 45350b has atmospheric chemistry that thermal models don't explain. Roman's directly imaged planet varies more than expected. The pattern suggests our models, while broadly correct, are missing pieces that matter in specific conditions. What pieces might be missing? For exoplanets, it could be magnetic field interactions with stellar winds, tidal heating that's more efficient than current understanding allows, or atmospheric dynamics in extreme temperature and pressure regimes that aren't captured by models validated on solar system planets. For Earth's magnetic field, it could be heterogeneities at the core mantle boundary that introduce instabilities, or coupling between different timescales of variation that amplify secular trends unexpectedly. For Atlas, it could be compositional differences reflecting formation conditions outside the range sampled by solar system bodies, or surface processing during its long interstellar journey that altered volatile distribution. The broader lesson is about the limits of theory when confronting complex systems. Models simplify reality to make calculations tractable. You assume spherical symmetry, or ignore magnetic fields, or treat convection as smooth and laminar when it's actually turbulent. These simplifications work fine for many purposes. They let you predict orbits, estimate temperatures, calculate basic properties, but they fail when the details matter, when systems are near transitions or operating in regimes where neglected terms become important. Science advances by recognizing when models break and figuring out what's missing. James Webb and Roman are showing us that exoplanet atmospheres are more complex than models based on solar system analogs suggested. That's exciting, not disappointing. It means there's new physics to discover, new regimes of planetary behavior to characterize, new connections between processes we thought were separate. Every surprise is an opportunity to refine understanding. The same applies to Earth's magnetic field and interstellar objects. Surprises indicate we're pushing into territory where simple models don't suffice, which means we're learning things that earlier observations couldn't teach. The pace of discovery is accelerating. Webb and Roman are delivering data faster than theoretical frameworks can absorb. Ground-based surveys are finding interstellar objects at increasing rates. Satellite constellations are mapping Earth's magnetic field with unprecedented resolution. Each new dataset raises questions that require new models, new simulations, new theoretical frameworks. The 2020s might be remembered as the decade when observations outran theory across multiple fields simultaneously, forcing scientists to acknowledge that reality is richer and stranger than our simplified pictures suggested. That's uncomfortable for researchers who prefer understanding to precede observation, but it's thrilling for anyone who appreciates that the universe still holds surprises, that we don't have everything figured out, that there's genuine mystery left to explore. Whether Atlas affects Earth's magnetic field or not, whether exoplanet atmospheric anomalies connect to magnetic field physics or represent entirely separate phenomena, the coincidence of all these surprises happening in the same few years creates a zeitgeist of uncertainty and discovery. We're in a phase where instruments are good enough to detect deviations from predictions, but theory hasn't caught up to explain them. That gap is where breakthroughs happen. Someone will propose a new framework that unifies observations, or develop models that capture the missing physics, or design experiments that test competing hypotheses. An understanding will advance, not smoothly, but in jumps triggered by the accumulation of unexplained data demanding explanation. The next sections explore how new techniques, especially artificial intelligence and machine learning, are being applied to these problems and what upcoming missions might teach us. Because if this video has a message beyond the specific story of Atlas and Earth's magnetic field, it's that we're living through an age where observation is revolutionizing understanding faster than ever before. Part 13. AI-accelerated geomagnetic prediction models. Predicting how Earth's magnetic field will evolve is one of those problems that sounds straightforward until you try to do it. The physics is well understood in principle. Convection in the liquid outer core generates and maintains the field through dynamo action. The equations governing fluid flow, heat transport, and electromagnetic induction are known. You should be able to simulate the whole system and predict future evolution. Except the equations are nonlinear, coupled, and operate in a regime where turbulence dominates. Solving them numerically requires discretizing three-dimensional volumes into millions of grid points and time steps into thousands of iterations. Even with supercomputers, simulations capture only decades of evolution at best, with spatial resolution that smooths over small-scale structures that might matter. Enter machine learning. Starting around 2020, researchers began applying neural networks and other AI techniques to geomagnetic data, treating the problem not as one of simulating physics from first principles, but as one of pattern recognition and extrapolation. Train a model on decades of satellite and ground-based magnetic field measurements. Feed it historical data showing how the field evolved. Let it learn correlations between current field configuration and future evolution. Then ask it to predict what comes next based on today's measurements. The approach doesn't replace physics-based models. It complements them, offering predictions that might capture patterns too subtle for human analysis or too computationally expensive for traditional simulations. Early results were promising. Machine learning models trained on magnetic field data from 1980 to 2010 successfully predicted secular variation trends through 2020, with accuracy comparable to physics-based models. That's impressive because ML models don't know anything about core convection or dynamo theory. They're purely empirical, learning patterns from data. The fact that they perform comparably suggests the data contains predictive structure that can be extracted statistically. But there's a catch. ML models are interpolators. They work well within the range of conditions they were trained on. When conditions shift outside training distribution, predictions become unreliable. The current rapid changes in the South Atlantic Anomaly might represent exactly such a shift, meaning ML predictions could fail just when they're most needed. More sophisticated approaches combine physics and ML. These hybrid models use neural networks to parameterize processes that are computationally expensive to simulate directly, like turbulent diffusion or heat transport at the core mantle boundary. The overall simulation remains physics-based, solving the governing equations, but certain terms are replaced with learned functions that approximate their behavior more efficiently. This lets simulations run faster, enabling exploration of parameter space and uncertainty quantification that would be impossible with pure physics simulations. Results from hybrid models in 2024 and 2025 showed improved agreement with observations compared to earlier simulations, suggesting the approach captures important physics that fully parameterized models missed. Could AI detect patterns in geomagnetic data that hint at external forcing? This is where things get speculative. If there were weak correlations between solar activity, cosmic ray flux, or hypothetically comet passages, and geomagnetic secular variation, ML models might detect them even if the physical mechanism is unknown. You'd train a model on magnetic field data alongside solar wind parameters, sunspot numbers, galactic cosmic ray flux measurements, whatever external variables you hypothesize might matter. If the model's predictions improve when those variables are included, that suggests correlations worth investigating. If they don't improve, the correlations either don't exist or are too weak to matter. No published study has found significant correlations between space weather and core dynamics on secular variation timescales. Solar. Cycle variations affect the ionosphere and magnetosphere but don't penetrate to the core. This matches theoretical expectations. But ML approaches might be sensitive enough to detect weak correlations that traditional statistical tests miss, especially if the relationships are nonlinear or involve time lags that obscure direct correlation. It's worth trying, even if results are likely negative, because the computational cost is low compared to the potential payoff of discovering unexpected coupling. One challenge is distinguishing correlation from causation. ML models can find spurious correlations in noisy data, fitting patterns that are coincidental rather than meaningful. Rigorous validation requires testing predictions on independent data not used in training, and ideally having a physical mechanism to explain any correlations found. If a model predicts that geomagnetic jerks correlate with solar wind pressure 3 years prior, but no one can explain why such a correlation would exist, it's probably spurious. But if correlations align with plausible physics, even if speculative, they might motivate further investigation. Another application involves predicting anomalies. The South Atlantic Anomaly's rapid growth surprised researchers partly because models didn't anticipate it. ML models trained on detailed spatial and temporal patterns might recognize precursors to anomaly formation or growth, enabling earlier warnings. This would be valuable for satellite operations and space mission planning, allowing more time to adapt orbits or harden electronics. Success here requires models trained on higher resolution data than used for global dipole predictions, capturing fine-scale structures at the core mantle boundary that seed anomalies. AI techniques are also being applied to paleomagnetic data, learning patterns of field evolution over millions of years from records preserved in rocks and sediments. These models attempt to identify precursors to polarity reversals or excursions, potentially revealing whether the current field configuration resembles pre-reversal states in the past. Results so far are tentative because paleomagnetic data is noisy and sparse compared to satellite data. But with large enough datasets and sophisticated enough models, patterns might emerge that inform whether we're heading toward a reversal or just experiencing a strong secular variation pulse. The philosophical question is whether AI can discover new physics or just accelerate application of known physics. Most researchers argue the latter. ML models are tools that find patterns in data, but they don't explain why patterns exist. Physical understanding comes from humans interpreting those patterns and proposing mechanisms. Still, AI-accelerated discovery is real. When models point to unexpected correlations or predict phenomena before they occur, they guide human attention toward fruitful research directions. Even if AI doesn't directly reveal mechanisms, it can highlight where mechanisms are needed, which is valuable in complex systems where intuition alone doesn't suffice. For the specific question of whether 3i Atlas could affect Earth's magnetic field, AI offers no special insight because the hypothesized coupling is so weak and the data so limited. You'd need simultaneous measurements of comet position, solar wind conditions, magnetospheric state, and core dynamics over many cometary passages to train a model. We have exactly one data point, which is useless statistically. But AI techniques applied to Earth's magnetic field evolution independent of Atlas are already improving predictions and revealing patterns that inform our understanding of dynamo processes. As datasets grow and models improve, we'll develop better tools for anticipating how the field evolves, whether or not external forcing plays any role. And those tools will be crucial as we navigate the coming decades and centuries of magnetic field change, whatever form that change takes. Part 14. Climate Magnetism. Interplay. Recent cryosphere and geothermal heat flux study. Earth systems connect in ways that cross disciplinary boundaries, linking processes that seem unrelated at first glance. Climate scientists study ice sheets and ocean circulation. Geophysicists study core convection and magnetic field generation. Rarely do these communities interact because their subjects operate on different timescales and involve different physics. But a study published in late 2024 revealed connections that blur those boundaries, showing how changes at Earth's surface can feed back to dynamics at the core mantle boundary through mechanisms involving pressure redistribution and geothermal heat flux. The work doesn't suggest climate drives magnetic field changes directly, but it demonstrates that Earth's interior isn't as isolated from surface conditions as traditionally assumed. The study focused on geothermal heat flux beneath Antarctic and Greenland ice sheets. Heat escaping from Earth's interior through the crust contributes to basal melting of ice, affecting ice sheet stability and sea level rise. Previous estimates of geothermal flux relied on sparse direct measurements and models based on crustal age and composition. The new research combined seismic tomography, showing mantle structure beneath ice sheets with improved models of heat transport through the crust, revealing that geothermal flux varies more dramatically than earlier estimates suggested. Some regions beneath Antarctica experience heat flux double the global average, concentrated where mantle plumes or remnants of ancient rifting bring hot material closer to the surface. Now consider what happens when massive ice sheets melt. The weight of ice depresses the crust beneath it, a process called isostatic loading. When ice melts, the crust rebounds over thousands of years as mantle material flows laterally to restore equilibrium. This redistribution of mass and pressure alters stress patterns in the crust and upper mantle, potentially affecting how heat flows from depth. Additionally, removing several kilometers of ice changes the thermal boundary condition at the surface. Ice insulates the crust beneath it. When it melts, the crust can cool or warm depending on ocean or atmosphere conditions replacing the ice. These temperature changes propagate downwards slowly, taking thousands to millions of years to reach significant depths, but they do propagate. Could rapid ice loss from Greenland and Antarctica, accelerating over the past decades, affect deep Earth processes on timescales relevant to human civilization? The traditional answer is no, because the timescales are too short. Ice mass changes happen over decades to centuries. Mantle convection operates on millions of years. Core convection operates on decades to millennia for secular variation. But the energy and momentum involved dwarf anything surface processes could contribute. Yet the 2024 study suggested that for regions where mantle structure is already anomalous, where heat flux is concentrated, surface load changes might matter more than simple scaling arguments suggest. The mechanism involves stress redistribution affecting melt pathways or volatile release in the upper mantle, which could alter local heat flux patterns more rapidly than bulk mantle flow. The link to magnetic field anomalies is speculative but intriguing. If geothermal flux variations at the core mantle boundary contribute to organizing core flow patterns, and if surface mass redistribution from ice loss alters geothermal flux on century timescales in specific regions, then there's a potential feedback loop connecting climate to geomagnetism. It's not a strong or direct connection. The energy involved in ice sheet melting is trivial compared to core convective energy. But if the system is near a threshold where small perturbations to boundary conditions can tip flow patterns from one configuration to another, then even weak surface forcing might matter. This is the same logic explored earlier for hypothetical space weather coupling, applied instead to internal Earth processes. For the narrative of this video, the climate-magnetism connection offers an alternative to external forcing that's still speculative, but more grounded in established physics. If Earth's magnetic field is doing something unexpected, maybe it's responding to changes we've induced at the surface through rapid climate modification. Ice sheets are melting faster than any time in the paleoclimate record, except during catastrophic deglaciation events. Ocean circulation is shifting. Crustal stresses are adjusting as mass redistributes. These are real, measurable changes happening now. Whether they cascade down to core mantle boundary conditions within decades or centuries, or whether such cascades would matter to core dynamics, remains to be determined. But it's a reminder that Earth's systems are more interconnected than disciplinary boundaries suggest, and that understanding how the planet works requires looking at the whole system, not just isolated components. As we navigate the coming decades of rapid environmental change, those connections might matter in ways we haven't anticipated, revealing that actions at the surface have consequences deeper and more far-reaching than we imagined possible. Part 15. Upcoming missions and what to watch next. The intersection of 3I Atlas's passage and Earth's magnetic field evolution in 2025 creates a moment worth remembering, regardless of whether any causal connection exists. But this moment is just one frame in an ongoing story that will unfold over coming years and decades as new instruments come online, new data accumulates, and new understanding emerges. Several missions launching or operating in the late 2020s will provide observations that could clarify the questions this video has raised, testing hypotheses about magnetic field dynamics, interstellar objects, and planetary systems in ways impossible with current technology. Let's survey what's coming and what to watch for as this story continues. For Earth's magnetic field, the European Space Agency plans a swarm follow-on mission tentatively scheduled for the early 2030s, continuing high-resolution mapping of field evolution. The current swarm constellation has been operating since 2013, providing the data that reveal the South Atlantic Anomaly's rapid expansion and the secondary minimum under Africa. Extending that time series another decade will be crucial for distinguishing between secular variation pulses and genuine transitions toward polarity reversal. Satellite magnetometry is the only way to observe core dynamics, translating field measurements at the surface back to their sources at the core mantle boundary through mathematical inversion. More data means better constraints on core flow patterns and improved predictions of future evolution. For planetary magnetic fields more broadly, the JUICE and Europa Clipper missions will provide detailed monitoring of Jupiter's icy moon magnetospheres through the 2030s. JUICE will orbit Ganymede, mapping its intrinsic magnetic field at high resolution over multiple years. That time series will reveal whether the fluctuations detected in recent data are persistent or transient, constraining dynamo models for small bodies. Europa Clipper will conduct dozens of flybys through Europa's induced magnetic field, mapping ocean conductivity and ice shell thickness with unprecedented precision. Both missions carry magnetometers and plasma instruments that will also characterize Jupiter's magnetosphere and how it interacts with moon surfaces and interiors, providing comparative context for understanding Earth's magnetospheric dynamics. The Nancy Grace Roman Space Telescope will continue direct imaging of exoplanets, characterizing atmospheres and variability that inform models of planet formation and evolution. Roman's coronagraph enables detection and spectroscopy of planets at separations where atmospheric dynamics transition from tidally locked configurations to more Earth-like circulation patterns. Observations over the late 2020s will build a census of young giant planets, revealing how common magnetic field-driven phenomena like auroral heating might be in explaining atmospheric properties. Every surprise in exoplanet observations challenges assumptions that feed into our understanding of solar system planets, including Earth, creating feedback between different scales of planetary science. Ground-based gravitational wave detectors reached new sensitivity levels in 2025, enabling detection of mergers and events at greater distances. While seemingly unrelated to magnetic fields and comets, gravitational wave astronomy provides tests of general relativity and strong field gravity that constrain fundamental physics. Any deviations from predictions might hint at new physics that could, in principle, affect how we understand gravity's role in planetary interiors or orbital dynamics. The connections are tenuous, but high-precision tests of fundamental physics occasionally reveal surprises that cascade across fields. What should you, as someone interested in these topics, watch for in coming years? First, monitor announcements about Earth's magnetic field evolution. The World Magnetic Model updates every 5 years, with the next version due in 2030. If secular variation accelerates further, or if new anomalies emerge, that will be headline news in geophysics communities and should propagate to science media. Second, follow interstellar object detections. As Rubin comes online, the discovery rate will spike. Each new object might reveal properties that challenge or confirm patterns emerging from Atlas, Oumuamua, and Borisov. Third, track developments in planetary missions. JUICE and Clipper results in the early 2030s could revolutionize understanding of planetary magnetic fields and ocean worlds. Also pay attention to AI-driven discoveries in geophysics and astronomy. Machine learning models are increasingly being deployed to analyze large data sets, finding patterns humans might miss. If an AI model predicts a geomagnetic jerk or identifies precursors to magnetic field anomalies, that will validate the approach and potentially provide early warning for future events. Similarly, ML techniques applied to exoplanet data, or interstellar object observations, might reveal correlations or classes of objects not recognized through traditional analysis. For those hoping Atlas might still spring surprises, the weeks following perihelion on October 29th are critical. If the nucleus fragments or exhibits unusual outgassing behavior, observers worldwide will be watching. Any deviation from expected brightness or tail structure will trigger intensive follow-up. If nothing unusual happens, that's also informative, confirming Atlas as a relatively normal comet despite its interstellar origin. Either outcome teaches us something about how comets behave under perihelion heating, and what properties vary between solar system and extrasolar formation environments. The broader message is that science is ongoing. The questions raised in this video won't be answered definitively for years, possibly decades. Magnetic field evolution operates on timescales longer than careers. Interstellar object studies require building statistics over many detections. Understanding planetary systems demands missions that take years to reach their targets, and years more to complete observations. This is normal in science. Patience is required, But progress happens, and understanding advances incrementally as data accumulates and models improve. The coincidence of Atlas's passage and magnetic field anomalies in 2025 will eventually be seen in context of longer-term patterns that clarify whether the timing meant anything or was pure chance. If you take nothing else from this journey through magnetic anomalies and interstellar visitors, take this. Earth is more dynamic than you probably realized. The solar system is embedded in a galactic environment that matters in ways we're only beginning to map, and the universe still holds mysteries that challenge our best understanding. 3i Atlas won't end the world. Your compass will still work tomorrow, but somewhere, 3,000 kilometers beneath your feet, iron is flowing in patterns that might be changing, and somewhere beyond the orbit of Mars, a visitor from another star system is beginning its long journey back into the darkness between stars, carrying with it secrets about worlds we'll never see. Both stories deserve attention, even if they never intersect except in the timing that brought them to our awareness, in the same brief moment of cosmic history we happen to occupy. The investigation continues. Stay curious, watch the data, and remember that the most profound discoveries often come from asking questions that seem absurd right up until the moment they turn out to be exactly the right questions to ask.